Okay, so let's get started. Before David starts with the first session of this reading group series, that will be just an introductory one, speaking about the book, the main principles, and to set the ground for the leading chapters. I want to start with just a few logistics. So this probabilistic machine learning reading group has been organized by us, David, Pablo, Dani, and Mario from the Institute of Mathematical Sciences. Uh, so the goal here is to learn together, to provide a structured way of getting to read the book all together and learning about this probabilistic machine learning thing. And yeah, before getting to David, I want to speak about the structure that this reading group will have. Sessions will be happening every other week. We can see here just the start of the schedule, and each session will be assigned a speaker. The speaker will give a talk for around 50 minutes, 45 to 50 minutes, and ideally that will be followed by 10 minutes of Q&A. Again, this will be up for the speaker, but the idea would be to hold the questions or make them through the chat and keep most of them for these 10 last minutes. Each session will be focusing on either a chapter or a section of the group of the book that we thought made sense to put together. They are already fixed in the schedule in the webpage, which you can look at, but everything here is flexible. So we welcome any feedback. We welcome any volunteers for speaking. And in order to do so, you can either use the Google Forms or send us an email. In the website, you also have some more resources, such as the schedule, the slides for past talks, the YouTube link in which we will be publishing past sessions, and also the link for the book, which is available for free online. The main announcements will be made through the mailing list, as we have made today. But we have also provided a Discord channel for more informal discussion, making questions, doing coordination, sharing feedback, more references, anything else really. And yeah, any feedback is welcome, as I've already said. So if there are any questions regarding all this, if not, I'll leave the ground to David. Okay, so David, I'll stop sharing and the floor is yours.
So thanks, Pablo. So do you see my screen? Yeah, okay.
Yep.
So hello, everybody, and thanks for coming. And also thanks to Danny, Pablo, and Mario for arranging this, which I think is going to be a lot of fun. Today, we are just going to give a brief introduction to notation and a brief overview of the key concepts that Pablo assigned to me. Just a brief motivation. I mean, let's say, local motivation. First, we have at CSIC, we have an AHAV connection in relation with artificial intelligence, and there's been going a few interdisciplinary discussions on topics related to PML. Then we've been doing some consulting for other institutes in which PML was required, and so we found that there was interest in our community. And then there is a couple of communities or a couple of programs at CSIC running on, which are Momentum and Allies. One is mostly a pre-doc, and the other one is a postdoc program. And there's a requirement for some training. Well, it happens that the SESIC and statistical ML courses are kind of oldie, so we decided to do something slightly modern, and we wanted to sort of build some kind of community, mainly within SESIC, but also in other parts of Spain, and as we have seen from the audience from other parts of the world. So that's what I'm gonna try to explain in like 45 minutes. First, some introduction on artificial and natural intelligence, which I will make it equivalent to PML. I will go through a very simple example for those who are not new. I mean, for those who are new, so that they grasp the basic concepts, and then like 3 or 4 core concepts, which will be. I mean, we will go in deep in more detail through the next weeks. But so I was told to talk a little bit on probabilistic graphical models as a basic way to communicate models or think initially of models. Some ideas on stochastic gradient descent, some ideas on MCMC and variational inference, and a bit on the road ahead. So I should say that I'm basically doing a brief distillation of Kevin Murphy's chapters 1 through 7, and I mean if you don't know the concepts, I mean you have like 2 weeks to revise it, and of course as Pablo said, we are open to questions. Okay, so I'm gonna um, first briefly recall what is an artificial intelligence system, which is basically software developed with one or more techniques, and is used, and for a given set of human defined objectives, it generates outputs, and such outputs are content, predictions, recommendations, and we shall be emphasizing decisions that are aimed to influence the environment. That's a definition from the European Union Artificial Intelligence Act, and it's kind of interesting that in the September 23rd version, the techniques that were let's say chosen included machine learning. So basically there were 3 groups. One referring to machine learning. The second ones were logic based, and there was a third group which included the statistics and explicitly referred to Bayesian statistics. It's kind of interesting that of course, I guess there were lots of lobbies acting there, and in the final version there were only machine learning related and logic related concepts. So the space in which we are going to talk is in artificial intelligence, and within the sort of most important current sort of techniques are machine learning, and within it, the most important are deep learning, and in turn, at the moment, the most important are transformers. So that's the kind of things that we are going to be talking. And all these months, we should remember that we are in the LLM rush. And that's a sort of map of relatively recent developments. But we should discuss that, well, there's life beyond LLMs, and that's part of the message that we would like to convey as well. So fixed ideas for us, machine learning refers to a computer program which learns from experience with respect to a certain task, or this could be several tasks, and a certain performance measure. And we say that this is happening if its behavior with respect to that task measured according to P improves with experience. I mean, to fix ideas again, some machine learning examples from some projects, type of projects that we have been doing, to emphasize two things. The first one is that uncertainty is almost ubiquitous in machine learning, and we need therefore coherent ways to handle it. And if we make predictions, we should make probably issue predictions with uncertainties about those predictions. And the second thing that we would like to emphasize is what is written in red, is that in the end, these things are going to be used to support decisions or to make decisions in an autonomous manner. And therefore, we need to integrate this uncertainty in such decision frameworks. So, as three examples, I've just put here, given the monitoring trace of an internet device, are we facing an attack? And if so, that's the question that we would be typically facing. And if so, should we stop operations? A person with Facebook likes will buy this type of beer, and if so, I mean, with which probability will he buy? Will she buy this type of beer? And should I send her my brand ad? If so, the robot that I'm developing performs this action. How will the user react, and how will the environment evolve? And if so, or given this, what should the robot do? I mean, so it's important to. I mean, we shall be emphasizing that there's uncertainty. There's uncertainty in the predictions. And given that uncertainty, what decisions should make the device that we are developing, the autonomous device, or the machine learning agent that we are developing? So, in many applications, we need to go beyond, and this means that basically, or quite frequently, we go. I mean, we just do performance of curve fitting, but we need to go beyond. We sometimes get satisfied when the model predicts correctly, but we need to go beyond. And one example would be in fraud detection. So that's a classification problem. And we focus on having few false positives and few false negatives. But actually, what really matters is whether we are minimizing monetary losses in the program. So more examples in reservoir system management. We make forecasts, but to produce more energy, mitigate floods, etc. In aviation safety risk management, we forecast accidents, but we do this to make sky safer, etc., etc., etc. So that's a kind of metric. So in that context, Bayesian inference provides a unified and coherent approach to problems of interest in typical problems of interest in statistics, inference, prediction, and decision support. Yet, the mainstream machine learning community focuses on maximum likelihood estimation or maximum likelihood estimation plus a regularization. But things are changing slowly, and in this change, we wanted to deep and discuss topics in probabilistic machine learning, right? So we are gonna make in these months an introduction to what is known and also to what is yet to be discovered. And the emphasis at the same time we shall introduce key concepts in Bayesian methods, but also mainly focus on models in machine learning applications, covering supervised, unsupervised, reinforced, and semi-supervised. Yeah. So so today is going to be an overview, as I said, and just let me go through a simple example to review the key concepts. First, we shall introduce probability as a measure of the degree of uncertainty with certain mathematical properties. And we shall be emphasizing the subjective interpretation of probability. This serves both as to introduce notation and also a review like very basic concepts. I mean, we shall be using conditional probabilities. So, what is the probability of a certain variable being having a value of y, given that we have an information on another information on another variable? Um, and this, sort of key tool will be a base rule, which says how do we update our beliefs of x given y, given the information y, and basically we'll use the prior probabilities, the model, and the evidence. Yeah. And let us illustrate this with a simple model. So that's a typical example. And we are considering recovery protocols for a computer after a cyber attack. We have one protocol, and we want to assess it. And for example, one possibility would be to be compared with another one. And suppose that we have had the protocol tested in 12 opportunities, and it has been effective in 9. And this means that, for example, the duration of the attack was less than 1 hour. Okay, so that with this example, we are gonna show the things that we are gonna be doing in more sophisticated problems in later weeks. So the model is very simple. There's n trials, identical and independent, let's assume. There's 2 results, and we are checking the number of successes in n trials. If the probability of a success in a trial, that's the parameter of interest so far, that's theta 1. The distribution of number of successes in trials would be a binomial, and for x equal 9, the likelihood in this case will be proportional to this quantity. So there were like 9 successes and 3 failures, so that would be the likelihood in this case. Right. The first approach, the standard approach in machine learning, in statistics, would be maximizing likelihood. So we just need to maximize this quantity, the likelihood, given these constraints. And well, it's easy to see that this is the number of successes divided by the number of trials. In this case, would be 9 divided by 12, 3/4. But this MLE has several effects, and we'll be discussing them. 0 successes, we would be saying that the estimator of success would be 0. Now, in this type of examples, we have some or many times, oftentimes, we have access to other sources of information about the parameter, and that's the prior distribution. That's what it's called, designated the prior distribution. Suppose in this case that we have little information about this parameter, and we decide to use a flat prior, right? We would update the information about the parameter given the observations, the 9 observations, the 9 successes, right, through Bayes formula. So we would multiply the prior. So the posterior would be proportional to the prior times the likelihood, and that would be in this case this quantity which we recognize as a beta distribution. Right, and this summarizes all the information available up to now, and we shall use it for several useful things. The posterior serves as prior for later studies. So suppose that we do five further applications with three successes. So the new posterior would be like this. So we would have the prior, the previous posterior, which is now the prior, times the likelihood, and this is has this expression now, and we recognize now a beta 13.6 with parameters 13.6. Right, but there could be other scenarios. For example, suppose that before we were saying we know nothing about the parameter, but suppose that based on previous experience, we estimate that around 80% of the times we are successful, and that bigger values are more likely. We could model this with a beta 4.1 prior, right? And the evolution would be different. So after the first successes, we would evolve to a beta 13.4, and after the three subsequent successes, we would evolve to a beta 16.6 parameter. And this shows us two things that we shall be using in machine learning. First of all is the sequential nature of base rules. So we update as we receive data. And another thing that always, but is as both processes observe the same data, or let's say as two, we have two experts with different initial opinions, but as they observe the same data, assuming that they are not assuming that they have not fixed ideas, they will evolve to, and we would have convergence in learning, and a consensus we would emerge. This doesn't happen always, but under, certain regularity conditions, it happens. So, as we said, the posterior has all the information that we require to solve inference, prediction, and decisions. Most of the information that we require. And to fix ideas, let us focus on the first case that we had a beta 10.4. So we can use this to find point estimates, for example, through the posterior mean, but there would be other possibilities, for example, the posterior median or the posterior mode, right? And we shall be using this sometimes. One thing which is quite important is that we can use interval estimates in the sense of genuine probabilistic interval estimates. So we can say that with a probability, for example, 0.9, the actual parameter is in an interval like 0.5 to 0.8887. We can use this also for hypothesis testing, for example, to answer questions like, is this protocol effective? For example, is the proportion bigger than 0.5? And we can compute the probabilities, etc. But most importantly, in machine learning is that we can use this for predictions through the predictive distribution. So we have illustrated, in this simple example, we could be asking what's the probability of more than 4 successes in 7 trials, and we would compute through the predictive distribution, which is illustrated there. And as I said, more importantly, we can use this to make decisions. Like, suppose that there's a second protocol, and in 10 opportunities, it has been successful in 6 times, right? It has its own success probability, which is theta 2 in this case. So we can model this, right, as a sort of joint model, where for the first protocol we have a theta 1 probability, for the second one we have a theta 2 probability. Suppose that we don't want to intervene in the data, and we use these uniform priors, and there's independent. And one thing that we could do is try to compute the probability that theta 1 is bigger than theta 2, given the data that we have observed. This is per se an interesting question, but it's also a good point that before all the computations could be done manually, analytically, but now we cannot do. I mean, we need to resort to, for example, in this case, we could resort to simulation, and this is going to be one key issue that we are gonna cover, is that in the type of complex machine learning models that we shall be facing, we will need to be ingenious, and we will need to be aware of a number of computational tools. We will need to be as well also that some of these tools are, let's say, in a scientific and technological limit, and we need to devise new tools. That's a sort of kind of urgent question. But I mean, just in this simple example, we need to, I mean, we cannot do it by hand, and we need to do computations through simulation, for example. Like the distribution of theta 1 minus theta 2 is not available in the books, let's say. And through simulations, we, let's say we do 1,000 observations from this beta 10.4 and from these 7.5 independent simulations. We compute the difference and count those that are bigger than 0 divided by 1,000, and we get an estimate of how likely is the first protocol to be better than the second protocol. And in this case, well, in this example, it was 0.772. And it seems that the first protocol is better than the second one, right? Everyone agreeing? So the answer is it depends, because these things have a cost. So we need to take into account the costs. So say we need to take into more precisely, we need to take into account the utilities that we get, or the losses that we get. It depends on the context that we are talking about. But we need to take into account if we implement a protocol and we succeed, or we do not succeed. And if we implement plan B and succeed, what are the utilities? And in the case is that given this utility structure, basically this is saying, in this case, the bigger the number is better. So in this case, the best situation is succeeding with plan B, because say, for example, that it's cheaper. The worst situation is failing with the plan A, because say it's more expensive. So we are failing, and we are failing with a more expensive treatment. Well, given these numbers, it happens that actually the best protocol is not the first one. Okay. This is a brief recap that you can go back, but I mean, what I just gave through an example is general. So we could do the parameter theta. What's the model? By yourselves later on, right? So basically all the computations done there, right? And moreover, I mean, as a sort of brief comparison, what in the classical approach, the parameters are fixed. In the Bayesian approach, parameters are uncertain, and that will be useful to provide a better picture of the uncertainties in our predictions and in our are involved in our decisions, and we will typically put a prior. As a sort of second stage, in both cases, we need to formulate the likelihood. And in the classical approach, we would typically maximize it. And it has many, so whether we use minimum least squares or whatever. Basically, these are principles of maximizing likelihood. In the Bayesian case, we would typically aggregate the likelihood with the prior to get the posterior, and with this we would perform, we would answer all the questions of interest. There's a recap. I mean, the previous one was based on the beta binomial, but the sort of the math. Or the general versions for general models, it's also, but you can check it. So we define the likelihood, we find the maximum likelihood, estimate what are the prior and how do you integrate. In all this, when you go through, the quantities that appear in red require some kind of integration, and it's quite important to remember that integration will be required for this business that we are going to go through. So how do we compute the base formula in general? Again, if we want to summarize in point estimators, we need to do in general additional integrations. To compute credible intervals, we need to do integrations, etc. How do we perform hypothesis testing? Forecasting, again, based on the predictive, requires integrating the sort of the observable variable given the parameter. We need to integrate it with respect to the posterior. So again, in integration, and quite important that this is sometimes, well, I would say oftentimes forgotten is that all these computations are used to make decisions. So we need to compute the utilities, either the posterior or the predictive expected utilities of alternatives, and then we need to maximize this. So these are the sort of kind of complex problems that we need to face. And this has been, let's say, sort of a brief description from a sort of a standard a statistical point of view, but we shall be reflecting all these methods on the core themes in machine learning, supervised learning, unsupervised, reinforced learning, and semi-supervised. Okay. So, like now in the remaining time, I'll just mention like 2 or 3 topics that we shall be covering in further detail in later weeks. So the first one is probabilistic graphical models, and we use this a lot to structure and understand problems before or trying to cover all the knowledge that the hypothesis that we have about a phenomenon of interest, etc. Right? And this is the kind of models that we shall be using. So we have like this kind of graph where each graph represents random variables of interest in the phenomenon of interest, right? And there's links indicating influence. Let's call it influence, right? So basically, influence means that the probabilities of a child depends on the values of the parents, right? And basically, this kind of graph provides the composition, which is based on the probabilities of the variable of interest given the parents. Like, for example, in this case, this is C has as parents A and B, so we would have a probability there in the model, right? We have directed and undirected versions. This also leads to I mean, as I said, this has besides the model, it has a hidden info. So there's probabilities at each table. There's tables of probabilities or models, more generally models at each node, and we use this to make forecasts, inference, etc. Given that we have observed certain data, we want to forecast other data, other variables. Just to illustrate, that comes from a project on cancer prediction. I mean, to illustrate, and we need to build in a project like this. We would need to build based on data, an expert opinion, the network, the distributions, and we would build the corresponding probability. And one thing, I mean, is that we could use this to, for example, identify risk factors. And one important thing is that through this approach, we are able to provide uncertainties. So we don't say that, I don't know, a certain risk factor here is 1.3. We just don't need this, but we say that with a very with a very high probability, this risk factor, for example, would be between 1.06 and 1.47. So that's one good point. And the other good point is that with these models, we can integrate these predictive models with decision models, and that's something that we shall try to emphasize. And that's one of the good things of this, that there is a sort of coherent integration, aggregating both predictions and preferences. Also, we can use this we can use this probabilistic graphical models to, like, let's say, have meta models of machine learning models. So we have here inference. Given the data, we try to infer. Given the data, we try to predict. Given the data, we try to find the optimal decision, and also we can model. We can use PGMs to model hierarchical situations. Finally, a brief mention to neural nets, which will be the sort of core class of models to be introduced. So first, optimization is an important operation. We mentioned it already like 2 or 3 times, but especially when we try to find out maximum likelihood or plus regularized, we use typically various versions of stochastic gradient descent, right? Just to give a flavor, I mean, we're representing here a sort of shallow or a non-deep neural network. So we have entrance based on the x's. We try to forecast the y's, and we pass the x's through some hidden nodes. So this is expressed like here. Then we combine them to make our forecast, right? So it's a combination between linear and nonlinear regression, and in the end, it's a nonlinear regression model, right? And the typical the standard approach. And we use this I mean, we shall use in principle gradient descent and backpropagation to estimate the gradients. If we introduce a regularizer, then we have, I mean, the same type of problem from a sort of mathematical point of view. And well, gradient descent basically means searching through, I mean, we compute a gradient, and we search in the sort of steepest direction. And when we move to sort of more complex architectures, deep architectures, so basically we have several layers. Um, um, when we do this, we could try to do the same thing, right? But we do it in a sort of a very large data regime. We see that the evaluating the objective function, evaluating the gradient requires going through a very large data set, and evaluating all the subterms. All these gradients require going through a large number of parameters, and the recurrence in this, recurrences in the forward and backward pass would be very complex. So we cannot do that. So we try to do gradient descent, but it happens, for example, that the gradient it does not even fit in memory, and it's very slow anyway. And we need to, the ways to do is go through a stochastic gradient descent. So basically, we get mini batches, and rather than doing through the whole data set, we do through mini batches, and we do the updates based on these approximate gradients. Under certain conditions, that's the stochastic gradient descent. Under certain conditions, which are pretty old, by the way, we can use reasonably successfully. We can fit those models. Important observations is that the batch now fits in memory, so these are slow. That there's many variants of this idea, and it's a pretty active area of working. And well, we don't need to differentiate by hand, but there's autodiff, for example. And now, just to compare, we shall be using those things, but just to compare and to finish, a PML with over neural nets, and the concepts here would be MCMC and variational inference that we shall be using. Now, first, basically, what is to be gained in this? All this. What do we gain? First, we get uncertainties in predictions. We get improved decision making based on the above on the uncertainty in predictions. We get some explainability via hypothesis testing. We get and so on, that kind of stuff. So that's useful. So just briefly, so how would be PML of a neural network, of a shallow neural network? So that was the neural network as before. That's the sort of basic ingredient. We need to add priors, and well, there's some justification of using these kind of priors. You can read them, but basically we put priors on all the parameters, which are the betas, the gammas, and the sigma in this case, right? And then the objects of interest, what we look for are the posterior, which would have this expression. And indirectly is the posterior. Directly, what is of interest is the predicted distribution. So what is the distribution given that we have observed? What's the distribution? What is the prediction that we make of y given for a new observation that is of interest, given that we have observed this data, right? This is, you can see these integrals, which are complex, and we need to resort to the type of tools that we will be seeing. For example, we have here a hybrid MCMC algorithm that we can use to assess the prediction, and you can see some vistas of what we change, what changes before. We in a sort of traditional can get, let's say, multiple curves like this and trying to assess the uncertainty. So that's useful for various purposes. And also we can get the distributions over the parameters, and this can be used for hypothesis testing and so on. We can incorporate architecture. We can incorporate uncertainty to the architecture. So, I mean, something that we could say is, I mean, should we use 5 hidden nodes or 1 million hidden nodes, or shall we use three hidden layers or 5 hidden layers? So we can handle this through variable architectures. And the good thing is that it gives us, first of all, it gives us some kind of ranking of the architectures, the probability of various architectures as expressed here. And we can use this for Bayesian model averaging, which allows us to improve predictions. And we shall see this later on. When we move from shallow to deep, we even need, this was the previous algorithm. We need to go to this type of our other algorithms like Hamiltonian Monte Carlo. And this even gets stuck given the type of problems that we are of interest at the moment. And we sometimes need to go through, I mean, and in this case, we must use the kind of variational base or variational inference that we shall be studying as well. Particular, this makes heavy use of information theoretic measures, and in particular, what is called the Kullback-Leibler divergence between two distributions. So this is used to assess whether a certain distribution is close. In this case, would be Q is close to another P distribution, and this is a key quantity, a key concept to be used in variational inference. So finally, the road ahead. So these are what we shall be seeing in the next 4 weeks. Unless, as Pablo said, somebody prefers to handle this, but that's what we want to talk. Some of the things that we have mentioned today. KM means that it's Kevin Murphy's the road ahead and some challenges I put here. So we need what are the limits of variational inference, new hybrids, new bright ideas from physics that we need to bring in to improve. Well, there's many topics of interest, including security of machine learning. Some references relating to machine learning and stats. Some references on machine learning, including some other sessions like this that we did before. Some readings on some other readings on Bayes per se, and on probabilistic machine learning. Remember, as Pablo mentioned, that we shall draw on Murphy's 2023 book. And that's it. So the next meeting will be the 19th, and this will be recorded and available soon on the website of the reading group. And I'm happy to, I don't know if you want to make questions, or will be available through Discord and so on, if we want in the next days.
Yeah, so thank you, David, for the very nice talk. We're very open to questions if you have any. Also, in terms of interest. So Mario Castro is asking, are there any references on that enigmatic sentence? Let me see. Bright ideas from physics. David. I don't know if you can answer that.
No, sorry. Thanks, Mario, because you're a physicist. So no, I forgot. I was going to be faster, but so basically, I claim, and as several of my colleagues, I mean, I claim that the sort of bright ideas on MCMC, etc., have come from physics. So Gibbs sampler comes from physics. Metropolis Hastings comes from physics, and Hamiltonian Monte Carlo comes from physics, actually. So I challenge my physics friends to discover the new bright idea.
Okay.
Yeah,
Thank you.
like you, for example.
Well,
Right. So my current bet is that the best thing is to hybridize variational inference and stochastic gradient MCMC until our physicist friends tell us what to do.
okay, thanks for the presentation.
Any other comments, or so I can check it in the chat, right?
Yes.
There's another comment there, yeah, by Jorge Gomez. Can you read it, David, or maybe I read it?
Can you read it?
Yeah, he's asking if we have other initiative like this one with Murphy book. The sessions will be accompanied by code. Yeah, so we'll probably follow the structure of Murphy book, and in that book they offer a lot of code. So we'll try to implement that code during the presentations to show some small examples on how things work. It will not only be over the more theoretical part, but also we'll try to see how to implement it easily. That's the idea. Yep.
Yes. But we did it like a couple of years before. We did one on let's call it plain machine learning, one on Bayesian, I mean plain Bayesian stuff, and one on causality. And we have put the links on the GitHub. And the idea is, I mean, the core will be Kevin Murphy's book, but as Pablo and Daniel mentioned, I mean, at some point we might, because somebody suggests, or we might use other papers, or yeah. So it's quite open as we say. But I mean, to give a sort of structure, we'll see it's like selected chapters. Also, we have selected chapters that are of more interest to us, but if you prefer to, hey, let's do in more detail chapter 15. So we are happy, and maybe we'll ask you to do chapter 15. But I mean, it's super long, 1,000 pages. So we have picked what is of more interest to us in our, and we thought that it would be more of general interest to everybody.
Yeah, so just as a reminder, the book is available online. Like it's very easy to download. It's public. It's not like fully finished. So there are some chapters that are shorter than they should be, but there's more information on several appendices. But for the important stuff that we will cover, it's very detailed in the book, so you can download it whenever you want. I'll make sure to send the reference. I'm not sure if it's in the web page, so you can follow that link to download it and have a look. So also for the next meeting, so you're more prepared to discuss more stuff. And yep, so if there are not any other questions, I think we'll wrap up here. Thanks everyone for coming. We hope to see you in the next session. And yeah, thank you for coming. Thank you, Wolfram. Thank you, Christina. Yep.
Bye.
Bye. Okay.